Right. So our second speaker for today is Pomerleano, and he's going to tell us about QH, quantum cohomology, and GIT quotients, shift operators.
Thank you so much, for giving me this opportunity. So I should say, like Umut, all of the stuff that I actually want to talk about is going to be more in lecture 2, all of sort of the newer stuff. And this talk is more going to be a survey of existing things, except there'll be one small result of mine and Konstantin's, but basically I'm going to go over some previous approaches to studying quantum cohomology of GIT quotients. So if you're bored in this lecture, you might consider coming to my second one. That's what I want to say. So I'll just sort of review sort of a classical theorem at Kerr-1 surjectivity. So this is sort of the starting point. So of what I want to talk about. So it's just about classical cohomology. So my setup, I always have a compact connected Lie group, and you have a compact, or you can relax that a little bit, symplectic manifold with a Hamiltonian G action, some moment map, and the classical theorem is that the restriction to the cohomology of so from the equivariant cohomology of your ambient space with Q coefficients to the equivariant cohomology of the moment level set with Q coefficients is surjective. And in this theorem, you don't actually care about what the stabilizers of your action are on the level set, but in practice, often you want to assume that you have finite stabilizers, so you can really form the symplectic quotient, or if you're in algebraic geometry, the GIT quotient, and get an orbifold, or at least a symplectic orbifold, or if it's free, a symplectic manifold. And in this context, so very recently, so I'm going over this because I was kind of pleased with it, even though I'm not sure exactly what it exactly it's it's not a big deal, but I'm kind of pleased with it. If you have finite stabilizers, then you get surjectivity by just inverting the order of all those stabilizers. And so in particular, if the action's free, one has surjectivity with Z coefficients. And the proof here, the reason I like it is that it gives a very elementary proof where you can actually see chromatic homotopy theory. Like, what's the point of chromatic homotopy theory? So let me sort of explain. So let me recall how the classical Kerr-1 surjectivity proof works. So you choose some invariant inner product, and you consider this norm squared of the moment map function. So this is not quite a Morse function, but Kerr-1 proved that it's good enough that you still get a stratification by descending manifolds, a Morse stratification, and then her main result is that this Morse stratification is equivariantly perfect. So you always, whenever you have this kind of stratification, you get a spectral sequence, and the claim is that in this case, the spectral sequence actually collapses. So how does it work? Well, you always have these kind of, if you have this stratification, you always have these, you can think of the spectral sequence as concretely kind of coming with these, you have cohomology of the pair associated to the, you introduce the stratum one at a time. You have the cohomology of the pair, and this, you use the Thom isomorphism to identify the cohomology of the pair with some shifted version of the cohomology of the stratum, and you want to prove that each of those, splits into short exact sequences. So these maps are always injective. and you know, so if you think about it, you know, going like this and then restricting back to the stratum beta is multiplication by the Euler class. So one way to do that would be to show that multiplication by the Euler class of the normal bundle is not a zero divisor. So that's one way you could prove that it's not equivalent, but that would in particular imply injectivity of this right map, which is basically what you need to, or left map, which is basically what you need to prove. And so there's a criterion for that, which is called the Atiyah-Bott criterion. So let's say you have a vector bundle, and let's say that over some space Y, so it's an equivariant vector bundle, and let's say there's a subgroup where the fixed point set of the action on that vector bundle is exactly the zero section. So it fixes the zero section, but its action, the representation on the fibers is all non-trivial. Then in that case, the representation is exactly, so then the claim is that the Euler class with Q coefficients is not a zero divisor. So you know, you can with Q cohomology, this is fairly easy to prove once you have the statement. So the point is basically that if you filter by you can first of all reduce to the case of a torus, and then if you sort of split the torus into your S1 and some complementary torus, and you filter by the degree of this, you know, you write your, because you can write your cohomology of your Y as being cohomology of BS1 tensor with this cohomology with respect to the complementary torus. And in terms of the filtration by the degree over here, the leading term sort of over a point in your manifold happening in the fiber of your bundle is basically going to be something like this, where this is a non-zero element of the cohomology of BS1. It's the Euler class of the representation. And because those are all your representations non-trivial, these Euler classes will always be non-zero, and that, you know, using a filtration argument, you can prove this statement here. So what happens over Z if you try to do this sort of naively? Then basically, you know, the argument fails because your representation could be, you know, sort of a multiple of some, you know, it'll be some multiple, some p-fold representation with a given prime. You could have torsion, let's say, and indeed you can see that over Z, if you don't do anything, if you make no assumption whatsoever, then then in fact, you know, you can cook up very easy counter examples to this claim. So for example, you take, I mean, it's not compact, but Kirwan's theorem over Q applies in this sort of setting. So you consider just a product action with weight 2, and so at the origin, or well, what do I want to say? If you double the action on both sides, the cohomology of your equivariant cohomology of mu inverse of 0 is like, has stabilizers Z2 times Z2, so it's basically just gives you this as the cohomology of B Z mod 2Z squared. And by the Kuninth formula, there's some odd cohomology here, so that cannot really, you can't have a Kirwan surjectivity. So you can't sort of just do so that shows you that there's something going on. You can't just do the naive argument. So what you do is you'll notice that when we do this argument, basically the only thing that enters into the whole argument is kind of the Tom isomorphism, basically. So it makes sense to try to consider what's happening in an arbitrary complex oriented cohomology theory. So these are just basically the most general theories where you have these Tom isomorphisms. So basically, the assumption is just, you can say it very simply, that your restriction from whatever your cohomology theory is to CP1, that you want that map to be surjective. And just from that axiom, you can kind of, that implies that you're, for instance, the cohomology of CP infinity to the M, that's just going to be the cohomology. It'll behave basically just like the usual cohomology of CP infinity, and you have Chern classes and so forth. So there's Tom isomorphisms and sort of usual package we need to do this argument holds. The most important thing associated to these cohomology theories are sort of their formal group law. So that tells you how basically how tensor product of line bundles, how does the Chern class of that, the tensor product of line bundles, behave? So that's in particular going to tell us how what the Chern class of one of these representations, what the representation should be. So that was sort of the key ingredient in the argument. So we have this formal group law, which is some power series in whatever your coefficient ring is, adjoins two variables x and y, and sort of standard cohomology theories, they the classical cohomology theories, they have these sort of well-known formal group laws. Sort of these are, geometrically one has sort of three kind of cohomology theories that are kind of defined geometrically, and these are the ones people know. So one has classical cohomology, complex K theory, and then sort of this universal complex-oriented theory, which is complex cobordism. And sort of the classical fact due to Quillen is that complex cobordism is sort of the universal cohomology theory, complex-oriented cohomology theory. So in other words, if you have complex orientations are sort of, so meaning these choices of classes of generators in E2 are in bijection with multiplicative natural transformations from MU to your cohomology theory. So any other, the point I want to make is that any other theory, there are tons of these complex-oriented cohomology theories, but they're sort of more algebraically constructed. So the ones that we need for this argument are constructed sort of algebraically from complex cobordism. So the first step, so basically from here, there's, one has to get used to the idea that your cohomology theory is not going to be geometrically defined, but it'll be defined sort of, one needs sort of to get used to doing algebraic operations in spectra. So, but once you accept that, there's sort of things you can do. So the first step is Quillen. So the first step was done by Quillen, who showed that if you localize at P, then you can sort of decompose the localization of MU into a bunch of copies of a spectrum that's called the Brown-Peterson spectrum that's a lot simpler. And this Brown-Peterson spectrum, what it does is it basically, the generators of it are sort of shifted. They're very spread out, actually. So if you know the coefficient of MU is also a polynomial ring, but there's sort of a lot of generators. Whereas here is sort of spread out very, very widely. So there's kind of less less generators, and the group law, so you can choose these generators, so that the what's called the P series. So what you get basically by combining, you have your kind of generator U of the cohomology of CP infinity, or E cohomology of CP infinity, it sort of, this group law becomes, very kind of explicit to work with. And then, from there, this is sort of has infinitely many generators, but you can also quotient out. So you can localize and you can quotient out. And there's so, just from this knowledge of this coefficient ring, there's a general theorem called Landweber exact functor theorem that says that you can develop, so we have an obvious sort of map from this to this. And there's a theorem that says you can actually just form a spectrum whose coefficients are exactly this. So it's called the Landweber exact functor theorem. It's a very powerful result. So there's a spectrum whose homotopy groups are exactly this, or stable homotopy groups are exactly this coefficient ring. And this cohomology, I think, was introduced by originally by Johnson Wilson, but really, as I said, like the natural construction of it is due to Landweber. So, I mean, all you really need to know about this cohomology theory is kind of its coefficient, and its group law is just kind of given by truncating this universal one up to order Bn.
Could you say a little more on this P series? What are, I can't even parse the symbols.
Say that again.
The P series.
P series. So
law F is the formal group law.
So you have this formal group law, and you just add, instead of, formal group law tells you how to add X and what's the Chern class of X or L tensor L1 tensor L2, but this is like what's the Chern class of L tensor L, the p-fold tensor product. Okay, so we're still not quite with what we want. So there's a nice further quotienting class, and these are sort of the cohomology theories that show up in seem to be showing up in symplectic. So we can, what people usually call Morava K theory is really, people usually call Morava E theory, is just given by, so completing this cohomology theory here at the ideal, basically sort of to make this sort of local. So this ring is, it's a polynomial ring, but you can, if you complete at sort of B1 through, or really you need to also complete at P, and then further B1 through Bn, then one gets sort of a local cohomology theory that's sort of easier to work with, a P local cohomology theory. Or you can, instead of that, you can quotient by the ideal which has everything, sorry, up to P, so you quotient by P, B1 up to Bn minus 1, and you get this what's called Morava K theory. So so that's one thing. So this is sort of what sort of, for instance, Mohammed and Abu Zayed, McLean Smith, they have developed Gromov-Witten theory and this cohomology theory, and they're variants of this where you, instead of dividing by you divide by basically the same generators, except instead of dividing by P, you end up dividing by P to the R. So so this is a cohomology theory that is, so it's sort of some nilpotent extension of the Morava K theory. What's sort of nice about this is that, well, so first of all, it has it's sort of the only cohomology theory besides maybe I'm not totally, maybe I'm not saying exactly. I think that this is true. It's the only cohomology theory besides cohomology with Eilenberg-MacLean cohomology with field coefficients that obeys a Kunith formula. So, but sort of more relevant for what I want to talk about is, or the result that I said at the beginning about integral surjectivity. The P series here simplifies just down to this. So by the we quotiented out. So we started with this sort of original thing, and then we quotient out everything that's sort of above and quotient out everything that's sort of above and below it, and we're just left with this very simple P series, which the most important thing for me is that it's actually non-zero. So so if you did this obviously with F over FP, your P series, your just Eilenberg-MacLean cohomology, your P series is trivial. But here you get something non-trivial, and that's going to be the key point. And it follows immediately from this that if you have a finite abelian group, then the Morava K theory of it, or really it's true for any of these homology theories, that the Morava E theory as well. This is a finite rank abelian group over the coefficients of over a point, and this is basically when people talk about why Morava K theory can be used to define Gromov-Witten invariance. This is basically the underlying fact, because this says that for orbifolds you get something that's kind of finite. So I mean, obviously it's more complicated because you're doing things globally. You want to actually develop Poincare duality in Morava K theory, but kind of this is a good indication that it's going to work basically. But coming to the statement that I started out at the beginning, the point is that just from this, the fact that this P series is sort of telling me the leading order term that one gets when one does this Atiyah-Bott argument, and before if I were doing cohomology, things with cohomology with FP coefficients, it could be 0, and then my argument was sunk. But in Morava K theory, the Atiyah-Bott lemma holds, and one gets that for any independent of what the stabilizers are, the whole argument goes through, and independent of what the stabilizers are on mu inverse of 0, one has surjectivity. So that's nice, but how do you kind of move back to cohomology? And this is the second very important property of Morava K theory, which is that if you think about the Atiyah-Hirsebruch spectral sequence, so this is what I was saying. These coming back to the beginning, the degrees of these VKs are the generators are really spreading out as K gets large. So so in particular, once I've gotten to, I take some large K or N, I guess, sorry, yeah, N, my Morava K theory is very highly periodic. So so it has a very high period. So as long as N is sufficiently large, so one basically needs that the degree of these generators is, if I have a finite dimensional space, the degree of these generators will be, I can make them larger than the dimension of my space, and the Atiyah-Hirsebruch spectral sequence generates automatically. So coming back to here, so let's say I have, one of my spaces can be infinite, but the other one is a finite complex. So that would be like this. this case, I'm imagining that I have this Borel space, and I have, my Y would be the Borel space, and I'm looking at mu inverse of 0, which I'm assuming, or mod G, which I'm assuming is a manifold, basically, as a homotopy type of a manifold. Or, in the orbifold case, at least, if I can work with the orbifold. Let's just say I can as long as my prime is disjoint from the stabilizers, it basically behaves like a manifold. Then suppose for every height I have surjectivity. All I really need is a sufficiently large height. Actually, that's all I need for this argument. Then map on cohomology is actually surjective. So I have surjections like this for any n. Actually, I just need n very large, larger than, so that the degree of Bn is bigger than the dimension of my space. Then this map on cohomologies is surjective. And this is the reason why I do things. We need this thickening because that allows me to do p to the r coefficients instead of just otherwise. If I just use classical Morava K theory, I would be doing things with just mod. I get surjectivity mod p, but I want to get it over integer, so I get surjectivity. So I do this thickening thing, and I get surjectivity modulo p to the r for every r, which is equivalent. Well, which tells me that I have surjectivity over z, and in fact tells me that my map is additively split. So this tells you this is stronger than just surjectivity. It says that not only if this is surjective, you actually have an additive retraction with z coefficients. So that was sort of maybe fast, but hopefully you can get the idea that this is sort of this idea that you can use other cohomology theories to give you things about integer cohomology is, one of the ideas of chromatic homotopy theory.
Yeah, I have a question.
Yeah.
The integral statement, are you saying it follows from just a single p or just from all p simultaneously?
Yeah, all p. I need all p. Yeah. I fit. Right.
Okay.
Yeah, from this statement for all p. Yeah. But you can actually now, do the same argument with other cohomology theories. So you can kind of go from, you can apply, there's a more general version of this that applies to any cohomology theory, any complex-oriented cohomology theory, and in particular mu. So it's more complicated. I don't want to explain it right now, but the sort of the strongest, if you integrate more of this chromatic homotopy theory, you actually get that the inclusion after you smash with mu is mu linearly split. So there's an mu linear splitting. But and you have to do something. So it's pretty easy. Again, you could ask whether this, maybe we're missing something, and maybe this is true just without smashing with mu. But it's pretty easy again to cook up very simple examples where you can use for example things like you can show that you don't have a splitting and stable homotopy. So this is really about this is only going to be true at the level of mu linear spectra. So it's really something about complex oriented cohomology theories. So okay, so I will use the integral Kerwan surjectivity result will be relevant to my quantum cohomology story. So there's a reason I explained it, but also because I think it's a good introduction. It was useful for me to see how you can use this machinery to say make some concrete actually can make some concrete statements. So hopefully that's interesting. Now I'm going to kind of switch gears to that's sort of everything I want to say about the classical Kerr-1 map. Now I'm going to switch to the quantum version of the Kerr-1 map. So, there's sort of two frameworks for doing quantum Kerr-1 maps. And one of them is due to a sort of an algebra geometric framework due to Woodward, and the other is a symplectic framework due to Fukaya. I'm going to go over both because I think, just like in Maxime's talk, this version, the version I want to use will be the symplectic version because I'm I guess a symplectic topologist, but this algebra geometric version, I think it could be very useful for some of this, for getting statements over the more algebraic versions of Gromov-Witten theory that we saw in Maxime's talk and are relevant for atom theory. So basically, if you want to define sort of the moduli space that's relevant for defining these sort of maps of, not quite cohomological, kind of cohomological field theories without metrics, is this complexified multiplohedra. So the open part of this, it will just be, so you'll have this kind of, the moduli space will be you'll have a bunch of sorry, there should be some n mark points that got left out of this definition. You have A1, but you have n mark points on A1. And you also have this non-zero translation invariant 1 form. And you want to consider the moduli space of these guys up to reparameterization. So you introduce this 1 form. And the open part of the moduli space is extremely simple. It's just the configuration space of points on A1 modulo C. So we can this has sort of a natural compactification into stable scaled lines. So where you allow sort of the domain to generate, and you have, in addition, you allow this scaling form to go also to 0 and infinity. So the condition that one wants is that, so you have sort of this, the scaling, so you have a nodal curve with n mark points. I'm thinking of Z0 as kind of my output point. That corresponds to the point at infinity previously. And we take sort of a section of this dualizing sheaf that's also allowed to be 0 or infinity. But the condition is there's a condition on this scaling. So basically, for any marked point, there will be one component which carries a finite scaling. And all the other components before this one will have infinite scaling, and all the components afterwards will have 0 scaling. So, as an example for what's happening is, if you imagine 2 mark points kind of colliding, then you have this sort of you think of these reparameterizations of these Mobius transformations that rescale it so that the mark points kind of come apart. But the scaling reparameters, so when you rescale the 1 form on that component, that 1 form will rescale the rescaled 1 form will converge to 0. So any kind of when points collide, the 1 form kind of naturally goes to 0. So this is some space that governs maps of cohomological field theories. And then for, again, just the open part of this Woodward's quantum Kerr-1 map. So basically what one does is one has one of these, so the data of the map will be a G bond. So I'm looking at the complexified group. So I'm going to assume that I'm looking at the case where the group acts freely on the semi-stable locus, and the data. So the data will be a G bundle over P1, one of these scaling forms, and then it'll be a map to the so it'll be a map. So we'll have a map from P to the associated space associated with that G bundle, so that U of infinity, so that the mark point Z0 maps to the open part of the variety, to the semi-stable. So this is sort of the open part of the moduli space looks like this, and there's again some compactification over these nodal scale moduli space of scaled lines, and the basic point of the compactification is that over the points where the scaling is 0, so the components where the scaling is 0, one has that the G bundle should be trivial, and all of the components where the scaling is infinity, those are supposed to map to the semi-stable locus. So I don't want to. So I just want to show you the form of the. It's, as I said, I'm just kind of reviewing this. I think it basically, well, I think it could be very useful for some of this blow up story that's been going on. So the outcome is a collection of maps. So if you look for any number of mark points, you get maps from this. You can define maps from this equivariant quantum cohomology to the quantum cohomology of the quotient, and then from this map you can cook up a formal nonlinear map, which is just given by taking all these maps and just applying, kind of doing something similar to the Mark-Cartan construction. It's something I don't know exactly what to say, but you just form this series, and that gives you a nonlinear map between the quantum cohomology, the equivariant quantum cohomology of M, and the quantum cohomology of the quotient. And then the theorem is that if you look at the formal derivative, we want to think of this map as being a map between the underlying spaces of the Frobenius manifolds, and the tangent at each fiber we have a multiplication, and the theorem is that the formal derivative is a ring homomorphism so that'll be between the tangent space here will be the bulk deformed product here, and it'll map to the bulk deformed product of this quantum cohomology of the GIT quotient. And one thing to say is that in general, there's so scaled lines themselves. We need at least one mark point to think of the moduli of scaled lines. But these maps we also allow n equals 0. So in particular, 0 here will be sent to some. So it's not just this map doesn't send 0 to 0. So there's some even at 0 that's moved to another point in the Frobenius manifold. So this is sort of I guess probably one should think that this gives a map of in the modern terminology, a map of these F bundles. But what I want to say is I believe that at least part of Iritani, the sort of first step of Iritani's in his blow-up formula decomposition. The first step that sort of relates equivariant quantum cohomology, it could be done much simpler with this. It should be much more conceptually with this map. I don't think anybody's looked at it, but it should be. I think he has a very similar map in his theory. But I want to look at this from a symplectic point of view, and from the symplectic point of view, one wants to consider a much more sort of general problem. So let's say we have a Lagrangian. Again, I'm assuming that the action is free on mu inverse of 0. And I want to ask how the equivariant Floer cohomology of L is related to the Floer cohomology of L bar. By L bar, I just mean the quotient Lagrangian. And the answer in Floer theory comes from the theory of Lagrangian correspondences. So there's a moment correspondence, and that's just given by points in M cross M bod mod G, such that the second coordinate is the reduction of the first, and that's a Lagrangian submanifold, and basically the general theory of quilted Floer theory allows me to construct, in the simplest cases, allows me to construct an A infinity bimodule over these two algebras. So the idea here is similar to the Fourier-Mukai transforms in algebraic geometry. So if you have the basic geometric idea is that I look at sort of maps with a quilting property. So I'm imagining that so I have two maps here, U tilde, and this U tilde will be a strip map upstairs. So it would be a map from, say, -1, 0 cross R.
I'd be really surprised if they can see that from the back.
Okay, I can try to make it bigger, but I need to maybe erase. Well, I don't even need to erase what I'll try again. How about that? So, better? No,
It's okay. I can see it.
I see. All right. Yeah. Okay. Well. All right. So I'll just try, and then people can ask me later. So we have the quilting property. So you have a map from. You have two maps. So you have your first map, which will be a map from -1, 0 cross R into your upstairs manifold. So this will be a J holomorphic map like this. And your second map will be U. So this will be U tilde, and U will be a J holomorphic map into the quotient. And they have to satisfy a quilting condition here. And that quilting condition is basically that the product map should lie on that Lagrangian correspondence. And so along this line. So this should map into this, what I called, I don't know how it went back, this L mu. So this here will lie in L mu, meaning that, which means that this map restricted to 0 will be in this L mu. And the idea is that I can, on each side, I can put a bunch of, further intersection points on each side. And what this gives in Floer theory is the structure of an A infinity bimodule over, if you do things equivariantly, will be on this side, it'll be the equivariant, I can make this a module over, these intersection points will correspond to generators of this Floer cohomology, and on the other side, this will correspond to things in the quotient, and I get this A infinity bimodule. Except that, the way one always proves things in Floer theory is by looking at what are the possible degenerations. So here I could have something which bubbles off on this side. That would give me one piece of the bimodule relation, or I can look at things that bubble off on the other side. But there's another thing that can happen, which is that if my correspondence itself bounds disks. And so the difficulty is if this Lagrangian is, these are monotone symplectic manifolds, and this Lagrangian correspondence is monotone, then you really get this A infinity bimodule. But if that's not the case, so if there are disks here, then you somehow need to do something to kind of cancel those out. So this is sort of, right. And I'll get to that. I'll get to that in a moment. What the statement is. But let's say that we're in this monotone case. So in particular, we're going to assume that these are monotone or Fano symplectic manifolds, and this Lagrangian correspondence, which is a further condition on the moment map, is also monotone. Then this bimodule gives me an algebra isomorphism between so the equivariant Floer cohomology of that Lagrangian correspondence and its reduction. So the reduction, if you think about the reduction, what's the reduction of that Lagrangian correspondence? It's just the diagonal. And we all, from the very beginning of mirror symmetry, Floer cohomology, the diagonal is just the quantum cohomology. So in good cases, one has this map, this isomorphism, and one also has a closed open map from the equivariant cohomology here to the Floer cohomology of that Lagrangian correspondence. And if you compose those, this should be like taking this step of looking at the closed open map should be like taking the differential of the map of this nonlinear map. So let me just, let's see, what time should I end now?
10 more minutes.
10 minutes, what?
10 more minutes.
10 more minutes, okay. So this is like what one gets in the simplest possible case is just a map like this. But in general, what you need to do is, as I said, the problem is that the correspondence itself is obstructed, so it bounds disks. But so Fukaya, and so all of this idea for this sort of alternative view of the quantum Kerr-1 map is due to Fukaya. In a lecture at IAS, he never really published it, but later, some people worked on it, so let's say if you what they prove is that, let's say you can make this correspondence on, let's say you can find a bulk deformation that when you bulk deform, you can kill this obstruction. So you can make the Floer algebra exist after bulk deformation. Then what you get is a map of these. So if I have some bulk deformation here and I have my Lagrangian L, then that determines a bulk deformation of the for the downstairs quotient Lagrangian. And then so for any choice, what do we need to choose? We need to choose, sorry, this notation got all screwed up. I apologize, but we have a bulk deformation here. For any choice of these, then you get that will determine one over here. One gets an isomorphism as before. Yeah.
You're calling them bulk deformations, but they're mostly bounding cochains, or are they both at once?
Say that again.
Are they actually bulk deformations or bounding?
Oh, well,
cochains?
here they're bounding cochain. They're that's supposed to be the theorem, is that they're just bounding cochains.
Okay, because you say bulk deformed, but
There's a bulk deformation. Yeah.
okay,
Yeah.
that's both. Yeah.
That will be in a moment. But here you just have these bounding. Excuse me, my term. Yeah, these are bounding cochains, and that one has this isomorphism. And then the conjecture, which was part of Fukaya's original lecture, but we still don't have kind of any written. We don't know exactly. But the claim is that. So yeah, what Denis was saying is that these a priori these are just bounding cochains in the Floer algebra, but that there should be some sort of ambient bulk deformation of the category that makes this Lagrangian cochain, that makes this Lagrangian correspondence unobstructed. And then the claim is that this B should agree with this. So I said that in Woodward's quantum Kirwan map, 0 is supposed to move to some other. Even 0 is mapped to some other point, that this that bounding cochain should agree with this term, this image of 0 under Woodward's quantum Kirwan map. And then so Fukaya's student has explained how this should work under certain expected properties that haven't been written down for G-equivariant Kuranishi charts. But this is still kind of a foundational piece that's missing. But if that's the case, then what I said before was about one Lagrangian at a time. But one expects further that you can get an equivalence of the subcategory of all these Lagrangians, which are in the mu inverse of 0. And by sending them to their functor would send that Lagrangian to its quotient. Equivariant Lagrangian in mu inverse of 0, and by sending that to its quotient, you would actually get a functor on Fukaya categories. So there shouldn't be an equivariance here. I'm sorry, so what that would give you an equivalence between the subcategory, the equivariant category, and the Fukaya category of the quotient. Yeah.
What's lambda 0 here again?
What's what? Probably some type of what?
Bulk deformation.
What's that bulk deformation?
No, well, what's lambda 0 there?
Oh, lambda 0 means that you don't want to consider a thing. You want the bulk deformation to lie in the maximal ideal, to have positive energy. So this is sort of the state. So there's still a conjectural picture, but in my talks, what I'm going to basically, I'll basically rely on this original result in monotone cases, in this sort of simpler result, but I'll also get some further results conditional on this statement. So that's basically a good place for me to leave things for now. So my next time I'll sort of sorry, one more thing. I apologize for trying your patience, but my talks, what I want to do is, so these are these maps these quantum Kerr-1 maps is I want to explain how one can calculate their kernels. So to really get a ring presentation for the quantum cohomology of quotients. So yeah, so that's sort of the connection. So everything after this will sort of, these are the two things maybe one should remember from this talk. First part of the talk. So thank you.